binary wanted to convert things to binary, and it came out to be the wrong answer. Like, oh.
Well, you finally figured it out. All right, this is chapter 11, basic cryptography. Okay. All right, this is the multi-level approach. We have firewalls, we have network intrusion detection, we have security appliances, but then we can also add encryption. Okay. All right, well, so what is it? Basically, it's taking our data, mixing it up so no one can see it. Like I said, scrambling information so it appears unreadable. Okay. Transfer it into a secure thing, so secure mode. Steganography, we actually do a project in forensics on that. It's hiding something inside something else. You can hide stuff in JPEGs, you can hide stuff in WAV files, you can hide them in images, audio, video, all kinds of stuff, okay?
You know that's the scale.
Where? Image, audio? Oh, well, I didn't write it. They made the slides.
I know. I was just...
Oh, they made the slides, sorry.
I know. I was just...
Yeah, stenography. Why? Yeah, why is it steno... Well,
I guess that's okay.
Well, stenography or steganography? Well,
I
guess it could be either. Well, stenography is like, that's like court reporting.
Right.
Yes, it is wrong. It's steganography, not stenography. Yeah, the word's wrong. It's the wrong. It's spelled correctly, but it's the wrong word.
They use the lookup, you know, like the dictionary.
Yeah.
Oh, surely you meant this, not that.
Wow, stenography. All right, so in stenography, when you're doing closed captioning, no. All right. Here's an example. We take our message, we can encrypt it into binary, we can hide it in something, maybe like the Statue of Liberty, which again, I do examples in that in other classes. All right. The Caesar cipher ones are the first ones, way back when. What they did is they basically shifted the alphabet by 3. So an A got shifted over by 3. Okay? Okay? A to D, stuff like that. Started way back when. And so encryption says changes the original text into some secret message. Decryption gets it back again. Okay? Then we could also have clear text. It's stuff stored without encryption, which is a lot of stuff done nowadays. Plain text would be the data that's not encrypted. Then we could have some sort of key to use when encrypting our data to jumble it up, and we're going to see more about that. So here we can take our plain text message. We can encrypt it with a key, and then we could get ciphertext. Okay? Then we could transmit the ciphertext to wherever it's going, then decrypt it with a key. Could be the same key or it could be a different key. We're going to talk about that here in a minute. Then we end up with our clear text again. Okay, so pretty cool. Okay, so cryptography and security basically gives us confidentiality, integrity, availability, but it also gives us authenticity of the sender, depending on how it's done. We know who sent it, again, depending on which way you do it. Also gives us something new we haven't talked about yet, something called non-repudiation. I know you did it. Okay, so it provides that the user performed an action, or proves that the user performed an action. But not always true. What happens if you were to gain access to my key, my personal key? Now you can prove that Ken Dewey encrypted it, but you're actually proving that Ken Dewey's key encrypted it. You don't necessarily know that Ken Dewey encrypted it because someone could have got my key. Okay, so it's not always perfect. Okay, we just talked about all those. Okay, all right. Couple different categories of algorithms. First of all is hash algorithms, then symmetric and asymmetric algorithms. Hash is like MD5. I mentioned in the last class, I attended a class recently, and the guy was talking about hash algorithms. An example he came up with hash algorithms is like sausage. Like, what do you mean sausage? Because, well, you take a pig, you grind it up into sausage. You cannot ungrind that sausage back into a pig again. Which is true, you can't go backwards. So I guess it is like sausage. So that's a very weird example. Another thing you can think of is like a car windshield. So I could take your windshield and smash it to 1,000,000 pieces. You ever going to be able to put that windshield back together again? It ain't happening. Yeah, exactly. Humpty Dumpty, the same thing. Could not put them back together again. Good point. Okay. So it's used for creating a digital fingerprint. It cannot be used to reveal the original data. Basically, we can use it to verify that it came from the original data, but we can't produce the data from it. Okay? Used for comparisons. Okay? Examples of hashed in ATM. We have the PIN number. This number is hashed and stored. First of all, the PIN has 5 digits. Aren't ATMs all 4 digits? So why is that only got 5?
Mine's a 6 digit.
There it is, really? Wow. That's not fair. I want one of yours. Mine's 4.
All of it. I mean, I have like 4 or 5.
Yeah, and they're all 4. That's not fair. Who want your bank? What bank do you use?
Well, I hate to tell you, but Bank of America.
Oh, Bank of America.
Bank of America.
Oh, that's the problem. You need to have some foreign bank. No, just kidding.
Yeah. Well, it's funny though. ATM card's 6 digit for PIN number.
Right.
But every time I leave my county, they shut my card off because they think that I've been
Oh,
contacted.
well, you know, the other day I bought something online, and my wife bought something online, like close to the same time period, and they called me. I'm glad they do. I have no problem with that. Because, you know, I said, did you purchase this? And yep, okay, thank you. So I'm glad they do. The only problem is I'm getting ready to go to Spain. I need to call them and tell them I'm going to Spain, or else I'm going to be
You can do that.
out of luck. Yeah. Yeah.
I've done that. I called up. I said, hey, I'm going to be going through Oklahoma,
Yeah.
Arkansas, Texas, whatever. Name off. I'm sorry, we only can put 4 states in there. And then I get to, the first state I hit,
It's
and I'm
good.
putting gas in the car, and they won't work.
Nice.
What's the matter?
Oh, wow. Huh.
Actually, usually it's about the 3rd transaction in a given state.
Yeah.
Or whatever.
I got gas in Texas just recently, and it was Conoco, I think, with Fuel Man or something like that. I had to put in my zip code, and then I had to put in the phone number listed on the account
Oh, I never.
at the gas pump.
I've never had to do the phone number.
Yeah, that was the first place I've ever. It was some weird deal. It was like Fuel Man, enhanced security or enhanced protection or something. It was zip code and then phone number listed on the account. I'm like, okay. I'm glad they're doing that. But
Too, I typically, like, they'll shut me off. I'll call them.
Right.
What's going on? Hey, I called. I told them I'm traveling. Oh, we tried to call you.
Yeah.
Well,
That's
we
a-
tried to call because all that information's up to date.
yeah. Well, they're not going to be able to call me in Spain, so I need to call my credit card company. So, all right, but the number is hashed. The results stored on the magnetic strip, so if you were to get it, you would not be able to tell what it is. So you insert it, enter the PIN, and then they compare them. Okay? Here's our hashed value, and when you enter your PIN again, they do a comparison, and it shows that it's the same. All right. So, hashing should always be fixed size. So if I'm hashing 2 digits or 2 billion digits, I should end up with a hash that's the same length. Okay? No 2 things should have the same hash. If they do, that's called a collision. Okay? MD5 has been shown to have collisions. MD5 is the #1 hashing algorithm used right now. But they've been able to prove that it has a collision. Well, the collision is if you have a specific document of certain size and change this one specific value, you can end up with the same hash. Which is, what's the odds of that happening? Very slim. But just the fact that it could happen makes people skeptical. All right. So we have an original. This data set cannot be created to have a predefined hash. And then the secure resulting hash cannot be reversed. You don't want it where people can look at the hash and get your data back. You don't want to ever be able to get back to the original again. Okay? All right. It says it's used to determine integrity. I can prove that that is your document because if I hash it again, I'll come up with the same hash. If the document's been altered in any way, it won't come up with the same hash. Okay? All right, uses method authentication code. Okay, improves security, has some secret key, but basically it's to prove integrity of the item. Okay? Here it says you are hired. We hash it through our hashing algorithm, come up with a hash. Okay? Then someone transmits you are hired with that hash. Okay? But then someone changes it. So the original message is you are hired, but the man in the middle of the text, someone says you are fired. So on the other end, they get it, and you run the hash algorithm, and the hashes don't match. So what you need to get is the message and the hash to prove that they're the same. A lot of times you'll download software, which I think I can show you one. Let me see here. No guarantees, but I think it's on here. A lot of companies have the hashes up there. Let's say we're going to download this one. Come on. I think it's on here. Nope, darn, it's not on here. Well, heck. At one point, they had them up there, but some places will actually show you the MD5 hash. I'm surprised it doesn't.
Try Nmap.
Nmap? Let's see.
Nmap.com.
Is it com or org? Nmap.org. Let's go to download. Okay. Where's the downloads? I just clicked it. Well, I'm trying to find the download. No guarantees I can find it. Okay, let's get it for Windows. Yes. Yeah, naturally I can't find one. There's a lot of them that do. Naturally, the one time I'm looking for one, I can't find one. I know.
I downloaded something from,
SourceForge, maybe?
yeah.
Let's go to SourceForge. SourceForge, let's go. What are we going to download? Wow, there's so much stuff. What's Allura? Forge software for hosting. Well, it's not critical I find one here, but a lot of sites, and actually none of the ones I'm looking at today, when you go to download their software, they will give you a hash value as well. So what you should do is you should rehash the download and make sure you got the real thing. Okay, so pretty easy stuff. Okay, one program you can use is MD5 Summer. That'll do it. Oh, here we go. We're going to download Fuboti Automation Workshop. Okay, and it tells us the hash. Okay, so they're actually using this to generate hashes. MD5 Summer is what I like better. Okay, but this shows you the different hashes for the different algorithms here. Okay, all right. So let's talk about hashing. Does it give us confidentiality? No, because we're sending the original message, but we're sending the hash as well. So really, we're not encrypting the message. Does it give it integrity? Yes, because now we know that it's the original message because I can compare the hashes. Really doesn't give us anything else but integrity. And is that kind of important? Yeah. Yeah. I don't really care if you see that I got something. I just want to know for sure that it's really what I asked for. So, all right. Most common, MD5 or Message Digest. 5 is the current one. SHA-1 is the SHA-1 still, or is it SHA-2? I think it's SHA-1. Okay. We got Whirlpool. We just got all kinds of them. Then the password hashes. Password like MD5 is used for most passwords now. Okay. There's a couple different versions of MD. There's 5. Okay. Designed to address the weaknesses. Okay. The message length is padded to 512 bytes. Okay. And they tell there it is. Weakness in compression function could lead to collisions. Again, they've only been able to find one, I think. Okay. SHA-1, another one. More secure than MD. It's just not as popular. Okay. Whirlpool works handy for washing clothes. I prefer Maytag, but you know, but it's a recent one. Okay. Then we have the RIPEND, the Race Integrity Primitives Evaluation Message Digest. Okay, I don't see that ever happen. It's too hard to remember the name. Okay. All right, then we got password hashes. We got LAN Manager and NTLM. LAN Manager hashes was what Windows used in the past. LAN Manager is not case sensitive. Okay, NTLM is. LAN Manager was limited on length. NTLM is not. Well, you can have longer now. Does anyone know how Windows stores passwords? Oh yeah, in the SAM. But how? I mean, how did the length that it stores?
Their hash, they were like 7 and 7.
Yeah, it stores it in 7-character chunks. So if I have an 8-digit password in Windows, actually what I have is a 7-digit password and a 1-digit password. So is 8-digit really better than 7? Not really.
And if you had a 24 digits, it carried the first 7 and the last 7.
Yeah, it's crazy.
Say that again.
What? Windows stores passwords in 7-character chunks. 7 and 1 if you have an 8-digit.
Right, so if you have 8-digit, then it has to use 2 7-bit chunks.
Right, it has to use 2 7-bit chunks, but it can break the 1 faster because it's all padded.
It's all padded, yeah.
Right.
But
if I was to look at a password hash of a bunch of 8-digit passwords, and they're all different, they would all end in the same value because the 8 digits all padded with something.
I thought they,
Because if you run Loftcrack or something on an 8-digit password, I guarantee it's going to break that 1 digit nearly immediately.
yeah.
Because they pad it. But, it does work. They also have salt, not sea salt or anything like that. Salt is basically a way of taking your password and then I think there's 96 different versions of salt. So what they're talking about is taking your password and encrypting it with one of 96 different values. So even if I take the same password and encrypt it twice with different salts, I get a different value. So we talked about rainbow tables earlier, last chapter. But so if I take a password and I have salt, so now that one password now has 96 different variations of that same password. Makes them more difficult to break, and Linux and Apple use those as well. Okay. All right. Symmetric. The original one is actually the fastest one out there. Okay. DES, Data Encryption Standard, was the standard for years, hence the name standard. Made in 72, I think. Does anyone know the cipher it was based on?
Lucifer.
The Lucifer cipher. Does anyone know why it's called the Lucifer cipher? Because the algorithm was the DEMON algorithm. The demon algorithm. But not really. It was actually called the demonstration algorithm. But the software they were writing it on couldn't support that many characters, so they truncated it to demon. So it's actually demonstration. But since it was stored as demon, they said that's the devil. We got Lucifer. So it's kind of funny. Okay, triple DES is basically 3 times, but what it actually does is encrypts with one key, decrypts with a second key, then re-encrypts with the first key again. That's how they get 3. Still used today. It's very widely used. A lot of firewalls and VPN systems use it. AES, Advanced Encryption Standard. Anyone know the cipher that one's based on? The Rigendale cipher. Okay? AES was actually, DES was developed in secret. To this day, they still don't know why some of the things function in it the way they do, some of the S boxes. AES was developed in an open competition. We know every single thing about it. That's the thing about cryptography. You don't want obscurity, or secrecy to be your reasoning. Because if you go by secrecy and someone gets the secret, well, you're out there. So with AES, it was developed in an open competition, and it's still used today. I mentioned in a lecture I was giving one day that it can be used for top secret data. After I got done speaking, a guy said, I need to talk to you for a second. I'm like, okay. He goes, you're never supposed to say that. I said, what? Yeah, you're not supposed to say that it can be used for top secret data. I'm like, why? It can be. He says, yeah, but they don't want everybody to know that. I'm like,
Well,
okay.
It can be used for top secret data, but it has to be a hardware
Right.
scheme
Right.
on it.
So, but I was like,
So
okay.
That's not a secret.
I know, it's like, but
It has to be layer 1 type.
it has to be hardware based,
and
right?
use AES, yes.
Well, there's a whole bunch of other ones. There's a popular one. If you look at my encryption, my cryptography, computer security lectures, I talk about the veneer cipher. It's kind of a cool one, but when I went to my CISSP bootcamp class,
Is it a name?
it's the Vigneri. I was in a class, and the guy was talking about, yes, there's this, it's kind of, the CISSP, a very good certification, but it's very broad. It covers everything, but it's only half an inch deep. But he's talking about, yes, and there's an encryption algorithm called the Vigneri. I'm like, what? I said, it's actually the veneer. He's like, okay. Yeah, he just went on. I'm like, that was pretty fun.
Yeah, I had a guy that I hired one time that when the first week he was there, called Novel.
Novel?
Yeah,
Nice.
I'm like, you're gonna have to stop
It's a
saying
novel
that.
software.
You're gonna have to stop saying that.
Yeah. All right, but there's a bunch of other ones. Jack Bauer in 24, I think it was in the last season, we're trying to break into this building, and it's encrypted with blowfish, which is a true one. But it was funny, like, oh, wait a minute, I know the secret back door to blowfish. They're in. Yeah, whatever. Okay. So, symmetrics is the same key. Okay? So the same key is used to encrypt and decrypt. Because of that, it's very fast. Symmetric algorithms are very fast. So we have something, we encrypt it with a key, we get our ciphertext, then we decrypt with the same exact key. So it's very, very fast. Also called private or secret key cryptography. Okay. All right. It says two symmetric algorithms categories. Stream or monoalphabetic substitution. Stream is like it encrypts stuff a character at a time, takes a character and replaces it with a character. I don't know, just replace one. It's kind of like the Sunday password, whatever, the Sunday, it used to be a Sunday paper, had the little daily jumble in there. They replaced one letter with another. We also have the monoalphabetic, which is like the Caesar cipher. It used one alphabet to encrypt. A little bit easier to do. Here's our stream cipher. We replaced the T with a pound, the H with a ampersand. So, okay. All right. Here we go. Hollow alphabetic. It's a single plaintext character mapped to multiple ciphertext characters. Also could be known as polyalphabetic, but it's just doing multiple. Why are they calling it that? It's polyalphabetic. Well, all right. Either way. Now we can also transposition. We have our message, and all we have to know is the length, and we break it apart in columns. It's rearranged without changing them. So if you look at the message there, the message is APR of it was achieved by our what? Action unit? Okay. But what we did is we got a length of 9, and we just read down. So we actually, the encrypted message is AAO, PHR, so on and so forth. That's how you get the message. But it's just transposition. No big deal. Okay. They talk about binary ANDing here, or this OR, one or the other, but not both. Let's make sure. Yeah. This is XORing. What they're doing is the final step in most ciphers, combine ciphertext with plain text to create a cipher key. This is what's called XORing. You take a 0 and a 1, you get a 1. A 1 and a 0, you get a 1. A 0 and a 0, you get a 0. And a 1 and a 1, you get a 0. So it's one or the other, but not both. Okay. I don't know why they don't call it, but it's actually called XOR. XOR. Okay. That's used afterwards. We also have something called the one-time pad. It's good for one time. Okay. Creates a truly random key. It says considered secure if the random secret key is not reused. We could also have a book cipher. Okay. Works on an entire book of plain text at a time. Okay. Books randomized. So not book, I'm sorry, block, sorry. Works on the entire block at one time. That's what DES does. Anyone know how big DES is? 64-bit block. But it's actually 56-bit because part of it's for parity. But what we do is we actually work on a block at a time. So, yeah, most of them are that. AES is block cipher as well. Okay. Stream is very fast if it's short. Disadvantages, a lot of computing power because I'm going to have to encrypt over and over and over. Block are more secure because the output is more random. Okay. That's what most of them are. Okay. All right. Now with this, we get confidentiality and integrity and availability, but we really don't know who it came from. Okay. Because if you got the key, you could encrypt it. And we really don't have any non-repudiation either. Okay. So we have DES, triple DES. Okay. A bunch of other ones out there. I talked about all of them a little bit already. Here's triple DES. We encrypt with a key. Then that's not how it works. They say they encrypt with the second key, then the third key. That is false. Actually, encrypt with one key, decrypt with the second key, and re-encrypt with the first key again. But it actually could be used different ways. So I guess this could be one variation of it. All right. AES, much better, was based on a competition designed to be secure well into the future. They're saying a system that could break DES in 1 second. So if you could come up with a computer system that could break DES in 1 second, would take 149 trillion years to break AES. So that's pretty darn quick. Very fast. Okay. Other, we have the Revest We have IDEA. We have Blowfish. I kind of mentioned that one. I'm not going into depth on these, but all right. And there's more. There's RSA. Actually, RSA is the next kind, but public key. So all right, let's get into asymmetric. So we already talked about symmetric. Symmetric has same key. Asymmetric has different keys. Okay. Its weaknesses are distributing and maintaining a secure single key among multiple is a problem. So with symmetric, we got to get that same key to encrypt and decrypt. So if I want to send something to Shalon, I have to get her that key so she knows what to decrypt it with. So that's a problem with symmetric. Asymmetric solves that. You have what's called a public key cryptography. Okay? Uses two related keys. I'm going to show you one up here. I'm going to go to keystore.pgp.com. Okay, maybe not. No, it's keyserver.pgp.com. There it is, keyserver.pgp.com. Now I'm going to search for Ken Dewey. kdewey@rose.edu. Okay, I'm going to search, and I got to put in my CAPTCHA. All right. T-U-R-N, Tunder. No, Tunder. All right. I did a search, and I found a key for Ken Dewey. Okay. I want to download this key. Oh, I bet I can't in here. Let's open it. Select a program. Use Notepad. Wow, I actually downloaded it. Very nice. I'm impressed. All right. There is Ken Dewey's public key. Okay. So if you were to download this key and encrypt something using PGP, okay, this key is publicly, obviously I found it on the internet, so you could download it. There's only one person in the world who has the corresponding answer to this key. That would be me. So if you encrypt something with this key and send it to me, who's the only person in the world that can open it? That would be me. Okay? So anybody can encrypt with my public key. I'm the only one that can open it. Okay? So what does that give me? Well, first of all, you know who you get confidentiality because I'm the only one that can open it. But will I know who it came from? Not necessarily. Since my key is public, anybody could have encrypted it. Okay, we'll talk more about that. All right. Also known as public key, uses two keys. A public key available to everyone, which I just showed you. Private key is only known to me. Now, as long as my private key is kept private, we're good. If I start giving out my private key, well, then we got a problem with it. Okay. All right, we got our plain text encrypted with Alice's public key. We got our ciphertext, and we transmit it. So we transmit the cipher key, and Alice decrypts it with her private key, and now she gets the message. So Alice is the only one that can open it. Okay? All right, principles, we have a key pair, so we have two keys that work together. We have one public, one private, and it can work both directions. Now, what if I was to take my private key and encrypt something and send it to you all? Could you guys open it? Actually, you could. If you download my public key, you could open it. So why would I do that? Why would I do something, encrypt something that anybody in the world could open?
Then we know it came from you.
You would know it came from Ken Dewey. Basically, you're able to authenticate the sender at that point. Because I encrypt something with my private key, I'm the only one that could create that. That anybody in the world that can open it. Because you can get my public key. But you can prove it came from Ken Dewey. So that's what it gives us. Okay. Able verifies the sender. Okay. Prevents the sender from disowning it. I'm the only one that could have created it. So there's no way around that. Again, as long as my private key is kept private. You can also have integrity of the message. Okay? So here we go. We got our plain text. We hash it. We encrypt it with the private key. Transmit it. We have Bob's public key. Now they're actually, and then we basically get the message back again. Okay? Now with the digital signature, we're actually not necessarily encrypting the message, we're encrypting the hash. Okay? So the message is still going to clear text, but the message hash is encrypted, and that way we know that it never got changed. Okay? When the hash match, we're good to go. All right. So I talk about different practices. We're going to skip that, but it gives us everything here. RSA. Now, one thing it didn't mention. Yeah. Okay, we talked about me encrypting something with my private key and sending it to you guys. How can I do it where we know it came from me and I know that you got it? Well, I can encrypt it with my private key, but I can also encrypt it with your public key. So I download Eric's public key. So I encrypted with Ken Dewey's private key, and I encrypted with Eric's public key. So Eric receives the message. He has my public key, so he knows it came from Ken Dewey. But then he has his private key, so he's the only one that can open it. The rest of you, you grab the message. Well, you have my public key, but you don't have the second part. So you can't open it. You can say, okay, it came from Ken Dewey, I just don't know what it is. Okay? Where Eric could see it came from Ken Dewey. So now we know we authenticated the sender and the recipient at that time. Okay? RSA, Ravesh, Shamir, and Alderman worked on it. There's a book by Stephen Levy. There's actually two books. One's called Hackers. If you go to Amazon.com, search for Hackers by Stephen Levy, L-E-V-Y. Okay, the book, actually, let me show it to you. A picture's worth 1,000 words, so we're going to go show it to you. Let's go. Come on. There it is. Let's go to Amazon.com. I'm going to look for Hackers by Stephen Levy, L-E-V-Y. There it is. Okay. Right there. You should be able to buy this book for $2.54. Okay. Normally you can buy the book including shipping for under $5. Hackers by Stephen Levy. They say you should never buy a book new. Unless people wrote in it. I mean, why does it matter? So, all right. Excellent book. It's story format. Starts about with MIT, how MIT got started with the Model Train Club. And they actually talk about how MIT, when they first got their first mainframe that actually had a password on it, they were worried, the people wanted to get into it. Administrators wanted to get it. So what they told people is they put a notice. Hey, it's going to prompt you for your password. Just hit enter. It'll be easier that way. So everybody's password ended up being enter. Okay. Excellent book. It's a story format. But he writes another book called Crypto. Crypto, right here. Again, this one's used for 1 penny. So including shipping, again, it's going to be under $5. Excellent book. It talks about all these algorithms. It tells you, like, RSA, DES. It gives you the entire story about why they did this, how they came up with what they did. It's really, really interesting. I have it on my Kindle, and I read it in the gym. Because I tell you, you're on the elliptical or something, while you're reading a book, man, that hour goes by so fast. It's like, woof. So, yeah. Two excellent books, Crypto and Hackers, both written by Stephen Levy. But, yeah, they're really, really interesting. All right, so RSA, MIT, way back when. It's used by factoring two large prime numbers. They're very large, 200 digits in length. Still used today, has not been broken. It's been out since 1977. Isn't that awesome? Still used to this very day. It's used with SSL. If I was to use SSL right now, I guarantee it's got... Actually, let's go find something. Watch me lie and not be there. Edu. Let's go there. That should have a key on it. Come on. We're waiting for that high-speed DNS server to wake up. Wake up!
Saturday.
Saturday is very slow. Okay, I'm going to view my certificate here from Rose State. Okay? I'm going to go details of my certificate. All right, see that signature algorithm right there? It says SHA-1 RSA. So we talked about hashes already. So it's used SHA-1 with RSA. So I can see exactly which algorithm is being used. So obviously, RSA is still in use. Okay?
It's 1024.
This one, let's see how long this one is. It's 2048. RSA 2048-bit. That's the encryption it is. RSA 2048-bit.
That's the lowest you can get now.
Yeah, 1024 used to be the lowest, but yeah. I actually made a short lecture, which should be online. I talk about key space. Actually, let me see if it's up there. Should be up there. 2563. Let's see. Let me know if you see something about key space. AES. I got all my lectures up here. User encryption widely. DES part 2. DES part 1. Key space. This is a very short lecture. Let's look at this one real quick. Come on. Now let's talk about key space for a second. Okay, this is important. Okay, so I have one key. What's the odds I can open that lock pretty quickly? Yeah. Okay. It's pretty simple. I have one key, one lock, put the key in, we're done. Okay? Y'all agree with that? We're pretty much 100% of being able to open this lock. Unless that's the wrong key. Okay,
Yeah.
so we'll assume it's the right key.
Okay,
Yeah, we'll assume it's the right key. Now I got two keys. Still got one lock, but now I have two keys. Different keys, by the way. But so you can see my time has
Doubled.
increased.
Or
Okay. Now I got three keys.
so I have 33% chance of now guessing it.
A show on Fox Reality called Solitary. Have ever seen that?
Yes, that's crazy, man.
Where they had like a million keys and locks, and they had.
But I keep going here. Come on.
Okay. So
What if I
my
had
first shot
10
is going
keys?
down pretty quick. What's called,
Oh, I'm,
hopefully I did right. So let's talk about binary real quick.
hold on. Trying. What if I have 50 keys? You can see the more keys you have, or the bigger the key space,
Yeah, exactly.
the harder it's going to be.
All right. So let's talk about binary real quick.
What else do I go into?
Do this. I'll help you.
Oh, yeah, here's the possibilities.
It's
Okay.
not it's 2 times
So,
2.
key space of 1, you have 2 possibilities.
3 is 2 times 2 times 2. Maybe like DES or AES or something. You can use some
Come on.
force, and I can do 7,000 per second.
2 to the 16
Or
possibilities.
75. So, there's up to
Yeah.
25.
Okay.
There's up to 40. Look at that.
So with only a 40-bit key, or the key space of size 40, look at all those different combinations you could have. That's a bunch.
Millions, billions, trillions, and whatever that number is. But that's a trillion.
It's a large number.
Trillions or some number. So you agree that, so with a 40-bit key, that's quite a few times. So if I'm going to secure my whatever, would a 40-bit key work for me?
That's pretty darn good. I mean, if you think about it, people say, "Oh, it's only
You feel safe
1024."
with your banking data encrypted behind a 40-bit key.
No.
Here's a 56-bit key. Look at those numbers.
Look at that.
That's what DES is.
Which we're going to be using here soon. DES. You're going to go for a while. Yep.
Do
You
I
have to
have,
make this run.
do I have to hire that? Do I go higher?
But
I think
banking with that.
there's 128-bit key. There's a 256-bit key. Look at that. Look at the possibilities.
1024.
There's a 1024 key. That's a very large
That's what
number.
my PGP kids. 1024 bits.
Ours using,
You know, we think that it's only 100.
there we go. 2048. So that is the key size of the D2L system at Rosate. What that means is there's that many different possibilities. That's pretty crazy. So you think that's pretty good encryption? Sometimes people say, "Oh, it's only 1024." Yeah, it's only 2048. Look at all those different possibilities. It's crazy. All right, so that's lectures up there if you want to watch the whole thing, called key space. Okay. All right, we also have elliptic curve. It says users share one elliptic curve and 1 point on the curve. Kind of reminds me of calculus. If anyone ever took calculus in here? Yeah, it's fun stuff. It's pretty much what they're talking about. They share points on the elliptic curve. We're not going there. Quantum cryptography is another one. It's based on photons. Okay. I actually have a lecture on quantum cryptography as well, so you can go watch that if you want. So it doesn't depend on mathematics, it depends on photons. I don't know if you know what photons are, but it's like light. But with photons, when you view it, it changes. So you can actually detect when someone's breaking in. You can actually look for that. Okay. We have TrueCrypt. There's just a bunch of different ones. Okay. Using it, it says it should be used to secure data when data needs to be protected. Can be applied through software or hardware. Hardware is always faster. Okay. File encryption. They have. I mean, what about what does Windows 7 use for encryption? Anybody know?
AES.
Well, what's the technique it uses? It's called BitLocker. Windows 7 uses BitLocker, which is actually very good. It's one of the best ones right now. If you use that, you ain't getting the data out.
So it's pretty good. You can also use PGP, which is the place I showed you I got my key from. You can use PGP to encrypt an email, to encrypt a file, to encrypt a message, to encrypt an entire hard drive. We had an FBI guy talking at one of the meetings I went to. They say they had this guy in custody for some crimes, and they have his drive that was encrypted with PGP. They have not, to this day, been able to unencrypt it. Still to this day. Made by Phil Zimmerman. And if you read that book, Crypto, goes into really gory detail about PGP, how he made PGP version 1. And the NSA was pissed. Because they're like, whoa, you can't be doing this. This is too good of an encryption. Well, then he released PGP version 2, and they told him, do not release anything else. Well, he posted it on one forum. Then instantly it went worldwide. And they're like, they started to prosecute him. They're like, well, what good is it going to do now? I mean, it's already out there. It's not like we can pull it back. So they said, well, forget it. It's too late now. It's already out there. So it's kind of funny. They also have GPG, which is the free version. Well, PGP is free as well. Symantec did buy them out, but works pretty good. So they're both asymmetric and symmetric. They use both. We also have EFS with Windows. I attended a training class put on by Microsoft, and they were talking about EFS. They said, don't use it. It's funny, when they released, I think in Server 2000, they said, do not use EFS. Because the initial release of EFS, if you forgot your key, guess what happened? You ain't getting it. What happens if Shalon encrypted something with EFS and she left the company? The initial version, we're not getting that data back. They said it's too confusing for people to use. Exactly what they said. It's not that it didn't work. It worked good. Or worked well, I guess. But they were worried about people not being able to figure it out, not being able to use it. So now the newer versions actually have a recovery group which could recover it, but initially it didn't. Okay. Usually then it's DFS. It worked quite well. Now we have whole disk encryption. BitLocker is what Windows 7 uses. It's very good. Okay. Hardware encryption is always faster. Software encryption, software could break, could have flaws. Hardware could as well, but it's not as vulnerable. Okay. Okay. Cryptography embedded in hardware. There was a key, I forget, a USB key they used. It's not going to be in here, I don't think. But they were saying how it couldn't be broken. Someone actually was able to break it. They actually took the hardware, disassembled, and were actually able to find a. Oh, it's funny, but USB encryption. You can encrypt your flash drives. Okay. You know what? There's a program called TrueCrypt. Excellent program. It's if you go to search for True, it's like TrueCrypt.org or something. Come on. There it goes. TrueCrypt. Yeah, TrueCrypt.org. Free open source encryption. You can encrypt files, you can encrypt drives, and Brett was telling us a story about that last class we had with him. But you can encrypt containers, okay? You can encrypt entire hard drives, and you can encrypt containers inside of containers. So it's kind of cool. Inside there, you can create a folder that's like 40 gigs, and you encrypt the folder. Anything you put into that folder is then encrypted. So it's kind of a cool tool. It's free. You can play with that. Okay. There's a lot of different things to use. Hard drive encryption, and you can encrypt your hard drive, but it will slow it down initially. You might have to enter a password or some key. Because obviously, if you think about it, it's having to do mathematical calculations. There has to be a slight degradation in power. That's why VPNs are a little bit slower. Okay.
Have you seen that one video on creating the hidden hard drive, hidden operating system using encryption?
No. Using TrueCrypt? Ah. But I know you can create, yeah, I mean, with TrueCrypt, you can actually encrypt an entire drive, and it looks like one file or something. And you can actually boot to it and then run, that could be what you're talking about, and run stuff.
They create basically a container, and anyway, you have two passwords. The password gets you into the hidden operating system.
Right.
And the other one, and they tell you to use the other one some so it looks like it's been lived in, and then you have a hidden operating system.
Nice. Well, that'd be cool.
That'd be cool.
But TrueCrypt's a very cool project. I do have projects set up with all these tools. I have an assignment I use for PGP. I have an assignment I use for TrueCrypt. If you want them, I don't have them with me today, but I could send them to you. They're kind of cool.
I've got a TrueCrypt container locked at home.
Right?
Didn't want happy for anybody to crack
Oh. Yeah, that's a good one. You know, Brett was just saying he has a TrueCrypt container that he doesn't remember the password on.
This
Yeah.
video I was watching said your SOL, if you
Yeah.
forget it,
Yeah.
it's not an
Different.
algorithm.
Yeah, so you're pretty much out there. So don't forget your passwords. Okay. All right, hardware security module, they talk about, you know, this is cryptographic process. They're actually embedding cryptography into some of the newer chips. So a lot faster. Okay, that's the end of this chapter. All right, let me stop the recording.